Okay, so that wraps up standard enthalpy of formation. Let's go to Hess's law. Hess's law, sort of similar, takes advantage of the fact that delta H is a state function. So let's pretend I've got some chemical reaction, doesn't really matter what it is. I'm going from step A to step B, all right? And this is enthalpy on this axis here, delta H on this axis, energy. This is indicative of an endothermic reaction. So we might write this equation as A reacts to B. Delta H is a positive number. Okay, but what if it's the case that this reaction is very difficult to do, or maybe we can't do it for whatever reason. Maybe there's some physical reason why we can't do this. But what if there's some other reaction or series of reactions where I could go from, let's say, A to C. So this would be A goes to C, and then I can go from C goes to B. All right, and then in effect, the difference between these two is well, I should have drawn this correctly, sorry about that. Let me just erase this and redraw this with the line at the same spot. Okay, so there's my level B again. All right, and then let's draw this arrow a little bit longer. Okay, so what I'm saying here is maybe we can do this reaction A going to C, and that one delta H is positive. And then maybe we can do this reaction C going to B, delta H is negative, but the net result of A going to B, we have a new delta H value that's the exact same one as this one. Okay, if we're writing this in words, we might say, let's call this delta H1, delta H2, delta H3. So delta H1 is equal to delta H2 plus delta H3. Now you might be saying, well, wait a minute, that's a negative number. That'll get taken into account by whatever delta H is. Okay? But what this is saying is, I've now got a two-step process that gives me the exact same thing as a one-step process. It doesn't matter how I do it, because it doesn't matter the steps I take. It only matters the initial and the final state. So if I end up at B, if I started at A, end up at B, it doesn't matter how I got there, delta H is going to be the same whether I go directly or whether I take kind of a circuitous route. Now this one I've happened to chose C where it's above, it could be below. I mean, I could have a situation like this. A goes to B by way of some reaction where I have to go down to C first and then up to B, but I end up with the exact same value for delta H going up. Okay, does that make sense? We can take multiple paths to get to the same place. As long as we do that, the delta H's all are going to sum up to whatever it was as if I just went directly. Now, because of this last trick we did, the enthalpy of formation, we might even be able to just look up those values and figure out what my new delta H is. Okay, so I'm going to skip these problems here in the book. I'll let you try those, or those are in my notes. I'm going to just jump to this quote-unquote more complicated problem. All right, and I'm going to show you how to solve one of these Hess's law problems with several possible reactions. So the way these problems are set up, it wants me to find something, and I'm given some example thermochemical equations that let me get there. So this one says, find the standard enthalpy of formation of CS2 liquid given the following pieces of information. So let's break this problem down into whatever the heck that means. Find the standard enthalpy of formation of CS2. What does that mean? That means forming CS2 from its elements. So C plus S yields CS2. That would be the formation of CS2 from its elements. Now, these are solid materials, so they're a little bit tricky. We need to specify which state, because I said the state matters, state of matter matters. So the most stable form of carbon is graphite, and the most stable form of sulfur happens to be rhombic sulfur. It's not a detail you really need to worry about. Now, is this equation balanced? No, it's not. I need a 2 out in front of here. and I want to find out what's the enthalpy of formation of this process. I don't want to actually do the reaction though. Okay, I don't want to burn graphite and rhombic sulfur together and try to make liquid CS2. And I may not even be able to do it directly. I may have to go through several steps. So here's how you do this problem. So first thing is you need to find out the final equation you're getting to. Sometimes the problem will give it to you. This one doesn't. This one just says find the enthalpy of standard enthalpy of formation. You need to know that means forming it from its elements. But let's assume you've been given this equation. So here's how I like to do this. I like to set up a table. And I'm going to write C graphite plus 2S rhombic yields CS2 liquid delta H sub F equals, I don't know what it equals. That's what we're trying to find. All right, so some people love these problems, some people hate these problems. I think the people who like puzzles or Sudoku or something like that, they like these problems. The people who just want the answer, they're not so thrilled with this. But if you're a puzzle kind of person and you like Sudoku, you're going to like this kind of problem. So here's what I do for this problem. I look at the products that I have and reactants that I have. So I've got graphite and sulfur on the reaction side, and I basically line everything up with my arrow and say this is the reactant side of the equation and this is the product side of the equation. Okay? So then I go up to these equations that have been given to me and I say, all right, I'm looking for graphite. Do I see graphite in any of these equations? Oh yeah, I see it in equation number A. There it is right there. So the first thing I do is I say, which of these equations has graphite in it? The second thing I say is, which side of the equation is it on? Well, this one is on the reactant side. This one's on the reactant side. Great, that's what I want. I want it on the reactant side. So I'm going to rewrite this equation. I'm going to take this equation and bring it, take this equation and bring it down here. Let's see if I can scoot this over. Okay, so I'm going to rewrite it here. C graphite plus O2 gas, and I'm going to put the, I like lining the arrows up. Maybe I'm OCD or something. Yields CO2 gas. Delta H reaction is equal to, now the next thing you need to do is you check the coefficients out front. That one has 1, that one has 1. Okay, you're good. You don't need to change the coefficients. So because I don't need to change the coefficients, I don't need to change this. So this is minus 393.5 kilojoules. Okay, now if we quickly look at this, now think about it this way. Think about this whole thing as adding all the, anything I do up here, I'm going to add together to give me this. This is like an equal sign right here. Equals this equation right here. So right now, I've got graphite on the reactant side, graphite on the reactant side. I've got oxygen on the reactant side. Don't have it in my final equation. And I've got CO2 on the product side. And you might be saying, well, there's no CO2 here. You know, why? How's that helpful? All right, we're not done yet. So let's come up here and we say, all right, next thing, rhombic sulfur. Oh, equation 2. That's got rhombic sulfur in it. And that's on the reactant side. So I'm going to keep equation 2 in the orientation it is, but what's the problem that I've got? I've got a 2 out in front of here, and I've got a 1 out in front of here. So I will need to change that. So we're going to say sulfur rhombic plus another O2, line up the arrows, yields SO2. What the heck? Delta H reaction equals to minus 296.1. All right, but now we got to deal with this. There's a 2 here, so I need to multiply this entire equation through by 2. And remember, whatever you do to the equation, you got to do to delta H. So I got to multiply delta H by 2 as well. So now we've actually picked up 2 more oxygens, and we've actually picked up an SO2. We still don't have my CS2, and now we've got a bunch of extra junk on the product side. So we're going to take care of that with the last step. All right, so last step, CS2 liquid, there's CS2 liquid, but do you see the problem we've got? That is on the reactant side. I need to move that over to the product side because this is on the product side down here. So I can flip the entire equation around. So now I'm going to put CO2 gas plus 2 SO2 gas yields CS2 liquid plus 3O2 gas. I've got one of these, that looks good. But what happened? I flipped this reaction around. And remember, when you flip it around, I got to change the sign. So now it's plus 1072 kilojoules. Okay? Now, remember, an arrow is like an equal sign for each side of the equation. So if I look at this carefully, I can say, let's see, I've got 3 oxygens right here, O2 plus 2 O2, that's 3 oxygens. Oh, there's 3 oxygens right there. That'll cancel these guys. And I've got a CO2 right here. I've got a CO2 right here. Those guys will cancel because they're on opposite sides of the equation. And I've got an SO2 here, 2 SO2, and I got a 2 SO2 there. That'll cancel out. And the only thing left is C graphite, 2 S rhombic, and CS2, the thing I'm trying to get to. Okay? Do you see what I did? So let me recap what I've done here. I'm allowed to take these equations that have been given to me, this information that's up here. I'm allowed to take these guys and rearrange them. I can put them exactly as they are, like this one happens to be exactly the way it was up top. This one I had the same equation, but I had to multiply through by a common factor, multiply through by 2, which means I need to do the same thing to the delta H side of the equation. Or I can flip the equation around and I need to change the sign from a negative number to a positive number, negative to positive. And if everything worked out right, all these extra guys are all going to cancel out, and you're going to be left with whatever the original equation was that you were starting with. Now this is ridiculous. I mean, I've just made a complete disaster out of this. So let's look at this in a little more simple form. Okay, so here's those 3 equations that I've rewritten. Graphite plus oxygen yields CO2, 2 sulfur rhombic plus 2 O2 yields 2 SO2, CO2 plus SO2 yields CS2 plus oxygen. I've readjusted these and I end up with a delta H of formation equal to positive 86.3 kilojoules. Positive tells me it's endothermic, takes energy to make this stuff. Now, what's the point of this? I may not have been able to just mix graphite and rhombic sulfur together to get CS2, but I might be able to do some other steps which will allow me to make CS2. It may take 3 steps to do it, but I can calculate the delta H of this reaction because I can look up all those other things in the standard enthalpy tables. This tells us, remember, because this is a little superscript, that tells us that at 25 degrees and at 1 atmosphere pressure, 1 mole of this stuff is going to take 86.3 kilojoules of energy to make from its elements.